The purpose of this video, rather short, is to discuss examples of tensor-triangulated categories as a invitation or as an entryway into the theory of tensor-triangular geometry. And the point is that there are examples in several different areas of mathematics, and what I want to do is do that, just mention all those areas, or a bunch of those areas, the principal ones, and give you the examples in the various areas. Now, I will not go into the full constructions of those examples because it takes time and it can be involved. Some of them are very elementary. I will mention the easiest one, but the more advanced ones are a bit sophisticated. So let's start with commutative algebra and algebraic geometry. So let's start with commutative algebra. So let A be a commutative ring. And in that setting, and actually in all the examples, I'm going always to give you a small category and a large category. And the small category will be called K, like compact, and the big category will be called T, like triangulated. And so the big triangulated category we are looking at is the big derived category of the category of A modules. So this thing here is an abelian category. This here is an abelian category, and it's a quotidic abelian category. And you can construct its derived category, which is made of complexes, a category of complexes. Of A modules. So complexes, I assume all my listeners would know what a complex is. It's just a bunch of maps, such that when you do two of the differentials in a row, you get zero. And morphisms of complexes are the obvious thing, so maps in all degrees which commute with the differentials. But with one peculiarity with the derived category is that we invert the quasi-isomorphisms, that is the maps which induce an isomorphism in homology, and so you invert them. Inside that you have what actually turns out, and the K will always be the compact part of the big T, which is the derived category of perfect complexes over A, which up to equivalence is just the bounded complexes, the B is for bounded, a bounded complex of finitely generated projective A modules. So you look at such complexes, but in each degree you have a finitely generated projective. And it's bounded, that is far enough to the left and far enough to the right, you have zeros. And here the maps are just up to homotopy. Simply because quasi-isomorphism between such complexes has to be homotopy equivalence, so you can realize the category in somewhat more explicit terms. And this is these are triangulated categories. This is probably one of the simplest ones you can think of, and this would work for any ring. It doesn't have to be commutative. What you use commutative for is to define a symmetric monodal tensor product with the tensor product on those categories is just essentially induced from the tensor product of A. And technically it's the left derived functor on the derived category, if you want, on bounded complexes of projectives, finitely generated projectives. So, yeah, finitely generated. If you tensor two finitely generated projectives together, they stay. The product will stay finitely generated projective, and so you have a very explicit description of the tensor here on the homotopy category. Now you can generalize this example to in algebraic geometry. So if you take X to be a quasi-compact and quasi-separated schemes, and all schemes in this business are assumed to be quasi-compact and quasi-separated. So this is a purely topological condition. It simply means that the underlying space has a basis of quasi-compact. Quasi-compact open. So if you want the intersection of two affine, the affine subschemes are quasi-compact, and you just want that the space itself is quasi-compact and that the intersection of two affine remains quasi-compact. It's a purely topological condition. For example, to recover what we just said, the spectrum of a commutative ring will be such a scheme. And then you can do an analog of this. You can do a small category, which will again be the compact it's actually a theorem that it is coincides with the compact due to Neyman. So you have the big derived category of X, and here you have to be a little careful. It's not quite the derived category of OX modules. It's not quite the derived category of quasi-coherent of OX modules. It's the derived category of OX modules whose homology is quasi-coherent. So derived category of OX modules, of complexes of X modules with quasi-coherent homology. Of complexes of OX modules with quasi-coherent homology. And if the scheme is one notch nicer, if it's separated, then this is really the derived category of quasi-coherent OX modules. And the perfect complexes, they are just obtained by taking the complexes, those that are locally perfect. So they are in the perf of A for every affine spec A in X. That's a way of saying it. Really, the conceptual way is to say it's the compact object. Oh, by the way, what does compact mean in general? So an X in T is compact if the homomorphisms from X into a big coproduct is just the same as the coproduct of homomorphism from X into all the terms. So this, all the factors. So this is commutes with coproducts. And in particular, you assume that T has all coproducts. So the big category should be triangulated and with all coproducts. By the way, I'm not going to discuss the triangular structures on those categories, but on the category of modules or derived category of modules like these ones, really what the triangles are is they are the traces, what survives from the exact sequences of modules. And the tensor product is exact in each variable. So this will always be a feature. The tensor product will preserve, tensoring with one fixed object preserves exact triangles. Now, you might ask, well, why do we care about those big things, those derived categories? And, it kind of goes hand in hand with the modern development of algebraic geometry. And things like K-theory or homological algebra, in all those subjects, those categories are very important. And one of the early motivation was really in two instances. It was the push forward. So when you have a vector bundle, you have something very nice on a closed subscheme or on a given scheme, and you try to move it, to push it to another scheme. So for instance, just take as an example, a very watered down, oversimplified example. But let's think of this. Let's look at the spectrum of Z modulo P inside the closed piece. That's just one point inside the spectrum of Z. So I could call that A, and that thing here K. So that's associated to the quotient Z goes to Z mod P. and perhaps we call this thing I, and so you have an I lower star. So if V is a finite dimensional K vector space, you can view it as an A module. Okay, so it's just V again, but then A acts via this map. Okay, you see, I want to know how A acts on V. Well, just project it down in K and then let it act. Okay, so and the notation will be I lower star V. And but the point is that, for instance, if the dual, the K dual, let's be precise, so the K dual of V, well, it has same dimension, right? It's really a non-trivial vector space. If V had dimension D, then this dual would have dimension D as well, as K dimension, equal to that of V, right? But if you dualize over A, if you look at the homomorphisms over A of the same vector space but viewed over A, that will be 0, because simply this vector, this module is killed by P, it's torsion. So if you have any element here, it will be killed by P, so it will land in the elements killed by P in A, but there's nothing killed by P in A except 0. So that forces this dual to be 0. So it's a strange thing, because this functor is rather harmless, right? It's just saying, okay, I'm just identifying, if you want, the Z mod P modules of Z mod P as special Z modules, simply those which are killed by P. And then the dual gets lost in that game, right? So, but the observation is that, just let's even take an even simpler sub-example, take Z mod P itself. Then if you look at I lower star of V, well, it is Z mod P as an A module, but it's really in the derived category. It's really the same as the complex Z multiplication by P Z. It's quasi-isomorphic to this complex, right? So if you think of this module as sitting in degree 0, then if you would put here a little degree 0 marker, that would be I lower star of V. But then you would see, okay, it's actually a perfect complex in that case. And you'd say, well, why, if I want to dualize that perfect complex, what will happen? So you just dualize in every degree, you get a complex, you see all maps are, the dual is contravariant, so all maps are going the other way. And so you see, okay, you still have a Z in degree 0, but you have, after the degree 0 thing, you have a Z dual. So what you get is actually a complex, you put back the arrows in the correct direction, you would get something like that. Well, this thing here is in degree 0. So it looks very much like the other one. So this is actually isomorphic to what you started from, but shifted by 1 to the right. The complex I lower star of V had degree 0 here, and you have moved that thing to the right. So that's the inverse of the suspension in this triangulated category. In fact, if you had taken another example, if you had taken A to be, say, take some field K and take x1, xn, and take just K to be simply A modulo the ideal generated by x1, xn, what would happen is that you would get an I lower star of V. The dual will just be I lower star of V, but shifted by minus n. And here, really, if you want to, preserve the variance, it is really, in this very silly example, this is really kind of canonically isomorphic to V dual. So this is really V dual here. If you take the dual over K. So let me really emphasize that by doing it this way. So there's really a little dual here, if you want. That makes the formula more likely, because it's contravariant in V on both sides. And this is interesting, because this n here is really the difference of the dimensions of the two spaces the two spectra you're looking at, the two schemes you're looking at here. So the 1 here is really the difference between the cool dimension of this, which is 1, and the cool dimension of that, which is 0. It's the relative dimension of this morphism. And so that's one of the things that will appear in the Grothendieck duality story, which is the more systematic study of how the dual works with the push forward, this lower star construction. This push forward along I. And of course, it's a much more sophisticated theory, which involves the exceptional inverse image functor f upper shriek and the dualizing complexes and all that stuff. But all that stuff actually makes sense at the level of derived categories. Okay, so this very elementary example, which is not meant to teach you anything about Grothendieck duality, but it's just there to indicate that, you know, even from the very beginning of these theories, we observe, so the observations, well, one is that there are phenomena that occur, that make sense on derived categories, but not on the level of modules. We've seen above the dual as a module. The dual was losing all information, right? That was the A dual of the module itself was lost, was losing the information about V. But if you, and by the way, I took this example, but then this would be true for all finitely generated V, or for all V in dperf of K. Okay, again, I don't want to go into the details of that, but that formula will hold very generally. So this duality that you see at the level of complex is very, very nice, and in particular we see some geometric information, right? Some geometric information survives or appears in the derived category. Like, for example, the relative dimension in the previous example, right? The difference of the cool dimension of the two schemes. So that was coming up in the formula that we see at the level of the derived category. So you know, another area, another class of example is K-theory. In K-theory, the K-theory was born, if you want, in a paper of Borel-Serre, but was really writing up Grothendieck's theory of the Riemann-Roch, what was, you know, later became the Grothendieck-Riemann-Roch theorem, and where he also looks at a Floer star for vector bundles, very much like the I lower star we had above, and what happens on Char groups and stuff like that. But really, there already at the beginning, what happens if you take a vector bundle, you have an f from x to y, you have a vector bundle of x, you push it down, and everything is smooth enough and nice enough that when you push a vector bundle, you get perhaps not a vector bundle anymore, but you still get a perfect complex. And then what you would do in the Grothendieck group is look at the alternate sum of the elements in this complex, in this resolution. And that's really like in the very first paper on K-theory. That's like perhaps not the first paper on K-theory, but it's like, you know, a very important initial moment of K-theory. It's 1958, right? The Theorem de Riemann-Roch, by, as I said, written up by Borel and Serre, but it was Grothendieck's ideas. And so already there, in this very first paper, there is, well, the push forward that I was mentioning above, which is really particularly interesting because out of even a vector bundle over X, you don't get a vector bundle over Y, but you get a perfect complex over Y. And then you handle that through an alternate sum of the elements of the complex to get back to vector bundles because you work in K0 and that's allowed. But yeah. And just to highlight another important point of the theory of K-theories was Thomason-Troubaud paper in the 90s, where he developed the higher algebraic K-theory of schemes in algebraic geometry, and this kind of goes hand in hand with the development of let me say, more perfect complexes, more information, more theory of perfect complexes. In fact, very specifically, he understands what happens to perfect complex under localization, and this understanding allows him to say what happens on K-theory. So you see that K-theory, just like from the beginning and in the high points and in many other aspects, is very intimately related to triangulated categories. And it was, Neyman understood in the early 90s that you could not expect Waldhausen K-theory to factor via the homotopy categories, because there are some functors on homotopy categories which have sections, and they don't have sections at the level of K-theory, so you cannot have a functorial way of doing that. There's also work of Schlichting on that topic in the 2000s, and it's only very recently that Moreau and Raptis kind of gave the big reconciliation of all those things to the K-theory of derivators, revisited. But that's an important step also, where the connections with not just triangulated categories but enhancements of those was discussed. So if you want to have a look at that. Anyway, what I wanted to say is that why do I mention that? Is that because even if you don't care that much about homological algebra, I did not even mention really homological algebra as a motivation, which is also, in addition to homological algebra. So the techniques of homological algebra, Ext, Tor, and all that stuff, it's of course very useful in itself. So of course reflecting some of the geometry as well, like regularity and things like that. So when you see all that, it's kind of interesting to say, well, how much geometry of X survives in D of X, or in its compact part, d perf of X. And there was a kind of a negative statement there, or a warning statement, which was the work of Mukai in 81, published in 81, I believe in the Journal of Algebraic Geometry. Let me just check that on the fly. No, excuse me, in the Nagoya Match Journal, duality between d of x and d of x hat. So he gave examples of schemes, non-isomorphic schemes actually, abelian varieties and their dual, such that they are not isomorphic, but their derived category are equivalent as triangulated categories. And so that was kind of a blow, because it indicates that you cannot recover the scheme from the derived category. But this was messing up the not tensor compatible. And really the person who understood that the tensor was very important is Thomason. In his last paper in 97, he highlighted the importance of the tensor, not so much in terms of reconstruction. I don't think he was thinking in that way. He does not mention that in his paper, but he tries to classify the triangulated subcategories of the derived category of perfect complexes, and he says, well, maybe I can't, but I can classify those which are tensor ideal. So he classifies the tensor ideals of perfect complexes, and that's really a very important precursor of tensor-triangular geometry. And so, as a corollary, one of the applications of tensor-triangular geometry is you can prove that if d of x is equivalent to d of x prime, as tensor-triangulated category. So not only as triangulated category, but preserving the tensor, which you would expect if the schemes are isomorphic, of course, then the schemes are indeed isomorphic. And you can put perfect complexes in F, which is, I mean, it's clear that if you have the whole derived category equivalence, then you have it on perfect complexes by restricting to the compact part, but only knowing that would suffice to apply that. Okay, so much for algebraic geometry, and I hope this gives you, and I won't go in so much detail in the other examples. I'm actually going to browse pretty fast on the other examples. But I insisted on that one because, after all, it's called tensor-triangular geometry. It's not called tensor-triangular representation theory or tensor-triangular homotopy or something like that. So really, this idea that those tensor-triangulated categories should have some geometry in it should be really motivated from the geometric example, mostly, I suppose. So, and you could argue that seeing geometry in further examples is kind of a little miracle each time. Okay, what about modular representation theory? So what do we mean by that? Well, we are talking about G, a finite group. And you are looking at the representation in characteristic, in positive characteristic. And preferably when P divides the order of the group. I mean, by preferably, I mean particularly interestingly when. So I remind you there is a theorem of Maschke which tells you that if the characteristic is 0, or if the characteristic at least does not divide the order of the group, then Kg is semisimple. So all modules are projectives, all modules are injective, and the finitely generated ones, because of Krug-Schmidt, they decompose uniquely as a sum of irreducible ones or simple ones, and you can, once you have decomposed Kg itself, then with the summons of that, you can recreate all other representations. So the semi-simple case, is interesting, but it's rather easy. And what modular representation theory is about is the case where Kg is not semi-simple. So Kg not semisimple. And so what does it mean? It means that there are modules which are not projective. And so what you could do is say, let's look at the Kg module. The small m means finitely generated. You can say, let's look at all Kg modules, and let's mod out the projectives. What does it mean? Well, it means that objects are just Kg modules, but maps, if a map differs from another map by factoring via projective, then you declare it to be 0. So you say a map is 0 if this map from M to M prime factors via projective. And of course, in particular, the identity of all projective modules will factor via itself, and so it will become 0. So all the projective modules will disappear. And that is actually the additive quotient. And so this is, if you're wondering what this means, what this bar here means, it really is a quotient as additive categories. It's a universal category receiving the Kg modules in which the projective modules become 0. It's as an additive category. And the amusing fact is that this actually ends up being a triangulated. And the triangles is an amusing construction. I'm not going to go into that again because I just want to survey the examples. And again, you can look at the compact part in it, and the compact part will be obtained by the same construction where you only look at finitely generated modules and finite dimensional representations of a K if you want. Okay, as the group is finite. So that's the analogy what we had before. We have a big triangulated category, we have the compact part, and the big triangulated category is generated by the small one. I did not say that. That's another common feature of the two categories, is that the small one generates the whole one. If you close the small one under arbitrary coproducts and triangles, you will get the big one. And again, there is a tensor product, and the tensor product is the tensor product of a K, be careful, over the field, not over Kg, unlike what happened with the ring A in the first part. So you tensor over K, and you use diagonal G action. So it means that you decide that G on M1 tensor M2 in M1 tensor over K. So M1 and M2 are Kg modules. Well, you just multiply the first one and you multiply the second one. So this tensor product is nice because it allows you to, that's a consequence of the Frobenius result, it allows you to it passes to this quotient. If you tensor projective with any other module, it stays projective. And so these quotients have a tensor structure, and they are tensor-triangulated category. The tensor is compatible with the triangulation. Okay, so what kind of logic, what is the motivation here? If you try to look at the motivation, it's not like in algebraic geometry where you might say, well, perhaps those categories have nothing to do with the real initial problem of life and the universe, which is understand the scheme. Here it is life and the universe, because we want to understand how bad Kg is, how not semi-simple is it. So how not semi-simple is it? Well, it's exactly that which will tell you how not semi-simple. It will tell you exactly what modules you have which are not projective. So this is a rather precise measure. This is the measure. These stable categories. Oh, by the way, maybe I'll use a notation for that. The small s stab of Kg and the big S stab of Kg for the stable module categories. So these stable module category, the big or the small if you want, is the measure of the modularity of the story, of how non-semi-simple Kg is. Right? Now, of course, it does not recover the group itself, because you could have stab of Kg being 0 if P does not divide the order of the group. I said preferably it should, but even if you start with a group which does that, you will look at the subgroups, and maybe some of the subgroups will have order prime to P, so those will have no stable category. For instance, the trivial subgroup certainly has a trivial stable category. And in fact, also the restriction from G to H, well, it passes to the stable category, that's the good thing. But sometimes it can be an equivalence. Even if the groups are different. For instance, in the so-called strongly p-embedded situation. So when you intersect H with a conjugate, this has order prime to P, or except of course when G is in H. So for G not in H. And if that happens, this is an equivalence, but it really is actually not so bad, because it really is a situation where, in some sense, the modular representation theory of G and H are the same. That's what this is supposed to tell you, right? So the logic is slightly different here. We are there. We don't have to worry too much. So if you want an example of that, you can this happens, for instance, if for P equals 2 and G equals S3, symmetric group of 3 letters, and H any of the two CELO. So you take one transposition, and when you conjugate a transposition by anything else, you will get another transposition, but involving transposing two other letters, and then that would intersect trivially with H. So that's an example where the representation theory would boil down strictly to C2. Okay, let me not go too much into general theory here. I want to just say that this is an interesting invariant, and just make a little remark that, once you have this stable category, so we still have Kohl-Schmidt, right? So Kohl-Schmidt says every kg module, any finitely generated kg module, can be decomposed in an essentially unique way as a sum of indecomposable that works even in the modular case. And Kohlschmidt therefore descends to the stable category, to the finitely generated one. And so in some sense, knowing the decomposition of modules in there is the same as studying a non-projective indecomposable. So that's what I was saying before, right? This is really contains the information, and Kohlschmidt for the finite dimensional ones is pretty conveniently descends pretty conveniently to the stable category. Just it means ignore the projective factors, and that's how the stable category was born, right? People were doing that before realizing this was a stable triangulated category. They were ignoring projective factors and saying, oh, up to projective this is the same as that, but what does it mean exactly? And what it means exactly is they become isomorphic in the stable category, and for maps it's important to work this way. But the observation you can also do is that then if you look at this functor from the kg modules down to this quotient functor, you might have, so this is a tensor functor. Because that's how we create the tensor on the stable category. This one is an abelian category, this one is a triangulated category, whatever. You can still wonder, what are the invertibles, the tensor invertible elements, and why is it interesting? Because even if you think about this, trying to study the non-projective indecomposable, if you have an invertible element, if M is such that tensoring with M is an equivalence on the stable category, then when you have a representation, well, of course it's very useful, but in particular, if N is an indecomposable in this stable category, in this category K, then so are M tensor N for every N, positive or negative. You can translate, you can move around your indecomposable by tensoring, very much as we did, as we do in the semi-simple case. When you have one-dimensional representation, you can tensor it around. Your one-dimensional characters, you can tensor around, and it gives an action on all the characters, right? So similarly here, the same thing happens. So it's interesting to know, which guys are like that. And of course, because this is a tensor functor, those which are already invertible here will be invertible here. And so invertible simply means this is an equivalence. But there are more, right? So the tensor invertible in kg mod is rather boring. It's just the same as saying the dimension of M over K is 1. It's a one-dimensional representation. And so those are still invertible, but there are more, actually substantially more in the stable category, and that's very interesting because that's they are called endotrivial for a reason I'm not going to discuss, and their study has been very important in modular representation theory, and that's another area where tensor-triangular geometry and the methods of tensor-triangulated categories have been useful to understand some construction, create new construction and stuff like that. So yes, really what one wants here is to build an intuition which goes beyond saying, oh, there are things which happens in example 1 and example 2 which are similar. You want really to unify things. You want to say, oh, not only they are similar, but here is the reason behind that. What does it mean for general T or general K to do this and that? And certainly being an invertible is a rather general concept, a very elementary one. Okay, the third and historically much earlier example, so example number 2 was more recent than the algebraic geometric and the topological example. But in stable homotopy theory, there is a triangulated category. So here maybe I'm going to go a little bit faster. The triangulated category is the stable homotopy category. So this is the homotopy category of spectra, of topological spectra. So you can start with topological spaces and say, well, can I study them up to homotopy? And then you can observe that if they are, say, pointed spaces, you can suspend them. And you say, well, can I study them up to homotopy? And so spaces, if you want, up to homotopy. And then you say, with the suspension, which is the smashing with S1, inverted, formally inverted, if you want. Now that would be, if you do it exactly as this kind of points to, it would be the Spaney-Whitehead category, and you do it in a way that this category still has infinite coproduct, because that's important for Brown representability. And the compact part of that you can do with a purely Spaney-Whitehead construction. So you would just start with spaces that can be, so you start with finite CW complexes, spaces which can be built by attaching infinitely many disks to infinitely many steps from points, if you want. And then you go up to homotopy and then you stabilize, and you don't have to worry about doing spectra there. You can do a kind of a naive stabilization. And these are earlier examples of tensor-triangulated categories, earlier compared to the modular representation theory one. Now here, what is the logic? What is the motivation? The motivation is kind of studying spaces is way too hard. Studying all topological spaces is hysterical. Studying all topological spaces up to homotopy also is quite hard. And working stably, even for the homomorphism of the sphere and its suspension. So what the homomorphisms of the stable homotopy group of spheres, which are the homomorphisms in SH from Si to S0. So you stabilize, and it's really, which means the homomorphism of the maps up to homotopy from Si plus k to Sk for k large enough. These are notoriously hard and interesting objects which have connections with other areas of mathematics. And so these could be one motivation to study this homotopy category. And then the so-called chromatic theory is another ancestor. Actually, it is probably an ancestor of Thomasson's work. So it's probably the most, the oldest TT sapiens here. I mean, the oldest example of this theory. And it let me say very vaguely, provides, overall organization to the finite spectra, with the goal of studying those stable homotopy groups. The ultimate goal is that in this topic, but you don't have to be obsessed with that. You could say, okay, I care about these tensor-triangulated category, these stable homotopy theories, and this would be, if you follow that logic, this would be to Z. It's a bit like Z in commutative algebra. And again, to make that precise, I would need more structure than just a tensor-triangulated category. But all tensor-triangulated categories that appear in nature, which appear with an enrichment of any sort, will receive this one, via a tensor-triangulated functor. So the stuff that happens there is the most fundamental, like what happens in the integers is the most fundamental thing that happens in algebraic geometry or in commutative algebra. So that's another motivation. Another motivation, this is the source of lots of the theory, because people developed a lot of the triangulated categories and stable homotopy. The word stable homotopy theory is sometimes used to mean the study of those structures, those enrichments which give you the triangulated categories or something like that. And so this is kind of topological stable homotopy theory, this particular example here. But here also, as I alluded to before, this is very important to have a very big category here, because of the so-called Brown representability theorem, which is, as many things in this subject, results are born typically in this subject, and the Brown representability theorem has been generalized by Neyman for the general pairs like that, big categories generated by their compact part. And so, which tells you when some cohomology theory can be represented. That is, when is a cohomology theory of the form like that for a given E? Well, it has to send a coproduct to product, and basically that's it. And triangles have to go to long exact sequences, so it has to be a cohomology theory. And so, the very fundamental idea used a lot in the theory, and it's arguably one of the big reasons to look at these those big categories T and not just the compact part, even if kind of the organization or the spectrum or many things are controlled by the compact part. Knowing that there is this ambient big category is very useful for constructions. Okay, so this is not doing justice to this subject. This is a very deep and complex and beautiful subject on its own. Let me just say that there are equivalent variants. There are equivalent versions. So which would be to the previous one what the study of G spaces would be to the study of spaces. So K would be, let's say, SH of G, maybe the compact, inside SH of G. And that would be T. And, let me not go too much into that, but it would be very similar to what was done before, except that there is a subtlety in what we mean by stabilization. One is not stabilizing with respect to smashing with spheres only, which are just the non-equivalent spheres. One should look at spheres with G actions, and there are more spheres with G actions than just a trivial sphere, and so these are the so-called genuine spectra, and so that the classification here, the analysis of those categories is for those constructions, and the reason is that their behavior with respect to restricting to subgroups and induction and stuff like that is stronger when you do the genuine story. And in particular, we see in the Mackey-2 functor of all the SHG for G moving in finite groups or compactly groups, you see some information about the group and its subgroups that appear. And that's another thing that tensor-triangular geometry has produced here, is that we recover from not only SHG but the whole family for all G's. Of those variants, we recover kind of combinatorial or group-like information about G itself, which is very interesting, and which then makes this subject, the stable homotopy theory, a bit more like the first subjects, where you had a given geometric or group-like theory, and think of that as an invariant of it, and you would like to recover basic the fundamental information out of this tensor-triangular invariant. Whereas here, this was really not the logic in this example, because there is nothing. It's SH. It's not SH of something. It's not SH of X, etc. Now there are. I'm really going over time. I wanted to keep that short, and let me just, without explaining, say that. There is a topic which is called a motivic theory, where you can do so if S is a base scheme. For example, the spectrum of a ground field, which would be typically a perfect field for some, depending what you want to do. And there is a version. So what you want to do is to do kind of similar stories, but you want to study smooth schemes over S, smooth schemes over S. You want to study their homological properties, that's the motivic idea, and you want to make A1, this is A1 over S if you want, A1 a new interval. So you want to make A1 the same as X. You want to do the homotopy by using an algebraic form of homotopy, where instead of using the interval 0, 1, you would have perhaps instead or in addition to, you would have you would have spec z of t for a variable t as an interval. So it's like saying, okay, you instead of moving things in continuous families, we are moving things in polynomial families, and we say, okay, at time 0 and at time 1, we want two things to be the same. How can you make that work? Well, it's a bit complicated, but there is a kind of an algebraic theory, and there's a topological theory. Well, in the algebraic, it's called the derived category of motives. There's a little GM for geometric, but it's the compact part. It's meant to be the compact part of the big DM of S. Here I might have to throw in some characteristic assumptions to be safe. And there is a topological version where K is, well, let's simply write SH of S. So S is here not a group, but it's this base scheme inside SH of S as a big triangulated category. So this would be the derived category of motives. This is Voevodsky's derived category of motives, or motivic derived categories, which would be an idea to realize those Grothendieck ideas of creating motives in an abelian category, to realize them through triangulated category or through homotopy theories. And this is, again, a stable homotopy category, but it's a motivic stable homotopy category. So in both cases, you have each of those categories would contain an object X. Let's maybe write motive of X for every, they contain motive of X for every smooth schemes, at least, or actually for more general thing, but at least for smooth schemes of X, in a way that the motive of A1 cross X is isomorphic to the motive of X. So you make this homotopy that we wanted. And they have kind of coefficients, actually it's based on pre-sheaves on smooth schemes with values in staff. And so in the algebraic coefficients, let me say vaguely, they are derived in complexes, if you want. And the topological coefficients are in spectra, in spaces. And that's what makes the difference. So if you one cheap way of saying that is this one would be to this one what SH is to the derived category of, say, the integers. So again, you produce tensor-triangulated categories, quite remarkable. There are again tensor-triangulated categories. Again, the big one is compactly generated. I might, as I said, need to put some assumption on the base scheme to be completely safe here, but whatever. And again, you can think of that in different ways, but you should just appreciate that those categories not only depend on S, but they have those coefficients there, right? So for instance, this thing here depends on S, but it has the whole SH kind of in it as a constant, as the constant motives. And so you just need to be a bit careful that you can't hope to understand those categories before having first really understood the non-motivic one, the ones not depending on the base scheme, or that is the coefficients. But with this out of the way, you can still kind of think of that as saying, okay, well, these are invariants of S. How much of S do I see back in these categories? For us, that would be a natural question. And the tensor-triangular geometry of those categories is really just in its infancy, right? It's very early. It's very early to say anything about those categories. There is work of Martin Gallauer, for instance, developing those things, but it's quite early. And the motivation for those categories goes back to the work of Grothendieck on motives and application by Voevodsky to the solution of the Bloch-Kato and Miller conjectures. So the motivation here is kind of a bit like in the stable module category. These are intrinsically useful categories, and then you start being a bit intimidated by their sizes, and you say, unlike the stable module category of a finite group, which was what rather easy to define. There is quite some work in defining those things. And you might say, okay, well, maybe someone gives me a 100-page definition of those things, but then what? What do I know about those things? They are big monsters. Help. And tensor-triangular geometry is another thing, it's another thing that tensor-triangular geometry tries to do, is provide help on those big categories. Say, a bit like when we're looking at SH. SH can be intimidating. Is there some global, like we don't even know the homomorphism between the graded endomorphism of the sphere, of the tensor unit? That's pretty sad. But is there some global organization that you can see and that will help you understand those things? And that's another thing that tensor-triangular geometry does. And there are more examples. Let me just say, just using the words without any details here. There are examples for instance, in KK theory of C-star algebras. And there's a very nice survey by Ivo D'Ambrogio on that. KK theory of C-star algebra, and here there is also an equivalent version where you have a topological group acting on the C-star algebra. So you can combine the above ideas, but that's kind of a bit more towards towards analysis, towards differential geometry. There is the equivalence between the Fukaya category and the usual derived category of its mirror. So in the so-called homological mirror symmetry, there are of course lots of triangulated categories, but also the tensor structure is quite interesting, because on the variety side there should be a tensor. On the Fukaya side, it's not so clear what the tensor is, but it should be if they are equivalent. And once you know that you have a tensor, then you can use the reconstruction result of tensor-triangular geometry. So that's kind of another use of tensor-triangular geometry, is to say, oh yeah, knowing the tensor is a source of geometry, and if you want to produce algebraic geometry in some differential geometry situation, well, go for the tensor. The tensor will be. So it's it's another kind of mathematical use of tensor-triangular geometry, is to say, yeah, tensor and triangulated together will contain geometric information. So that's a guide in things. And there are lots of variations on those, even on the ones I've discussed above. And I've written a survey of in 2019, which is called a Guide to Tensor-Triangular Classification. And if you want to see more examples, more variations on those derived categories, stable categories, singularity categories, and stuff like that, there's lots of those variation on the theme. Okay, so one can look at all those examples and say, yeah, okay, that's just category theory, or that's just set theory. All those things are built with sets, and throw your hands up in the air and say, what can I do? Nothing. It's just different subjects. Or you could just start trying to say, maybe there's some unification that can be done. There's some common approach. But it's very important to appreciate the diversity of the examples in this theory. It is not a sophisticated way of doing algebraic geometry. It would not be useful, because algebraic geometry is more powerful than derived, or let me take this back. It's more powerful than looking at the derived category of the scheme. I'm not commenting on derived algebraic geometry. And it's not just a sophisticated way of doing algebraic geometry. It is a way of touching all those subjects at once in one approach, which has a geometric motivation. Okay, that's it for the examples.